Okay, we're going to go over a couple of questions I talked about this week. Um, First question is in Statistics Lecture 7. It's probability and at least one. And so we're going to take a quick look at number 20 here. A very common question. And if we read about this, they're saying we have a blood testing procedure. So this is a very common testing procedure. And what they're saying is blood samples from 6 people are combined into one mixture. So I'm going to take a look here and kind of draw a picture of what they want you to do here. So let me go back to this browser. I'm going to get the iPad up and running. And here we go. So they're taking blood from 6 people. So if you said, what does that look like? Well, we have person 1, 2, 3, 4. Looks like we have 5. This will be the 6th person here. And so what they're going to do with these 6 people is they're going to take blood and they're going to put it into this container. So I'm going to draw a picture of a container or a bin, however you want to look at that. They call that a mixture, by the way. And so blood from each one of these individuals gets placed inside this mixture. So I apologize for being a bit gory, but this is kind of the idea. I'll erase it. So I'm going to fill this container with really the blood of 6 people. Okay, so that's kind of the idea. So you have a mixture. And what they're going to do now here is if we go back and read that, right? So let's kind of make some notes. There's 6 people. And what they're going to do is they're going to test the mixture. They're not testing the individuals. They're testing the mixture. So 2 things can happen here. And I want you guys to know when they test this mixture. When they test the mixture, it can either test positive or it can test negative. That's what's going on with this mixture. It's going to test positive. It's going to test negative. Okay, so there's 2 situations for the mixture. It either tests positive or it tests negative because we're going to actually just test the mixture as opposed to testing people individually. So going back to what this says in the browser here, they're saying in a blood testing procedure, blood samples from 6 people are combined into one mixture. The mixture will only test negative. So notice this. These are the conditions regarding the mixture. It will only test negative when every individual tests negative. So let's see, the mixture will only test negative if all individual samples are negative. So yeah, so we want to make sure we know that concept. This tests negative when everybody tests negative. So we have to say all 6 individuals will certainly test negative, and that's going to give you a negative mixture result. And so I'll put that over here. We're going to move this. So your mixture will test negative or test positive. So we know this piece of information. And then here's what's important. we have to know when this mixture tests positive. And that mixture will test positive, ladies and gentlemen, when at least one individual tests positive. So at least one person will test positive. So that's an important detail. Now you might say, well, what if one person tests positive here, right? You get an individual and that person tests positive. Well, then the mixture will test positive. But that's not the only situation. There could be two people that test positive. And if that happens, the mixture will test positive. They can be three people that test positive. And if that happens, the mixture will test positive. And in fact, everybody can test positive. And that's why we say at least one person must test positive in order for the mixture to be positive. An important detail. Compared to the statement that in order for this mixture to test negative, everybody must test negative. Everyone, for the mixture to test positive, test negative. And so that's kind of what's going on here. So we have to notice those two situations, those two cases, because we're going to just end up testing the mixture. And so what happens now then is if we go back to the browser and we read this, it says if the probability now, here's the last sentence, if the probability that an individual sample tests positive, they should say the probability, and this is what the statement is, that an individual now tests positive is 0.12. So let's write this down. That statement is referring to an individual. So the probability an individual tests positive is 0.12. Now that's for an individual. That's not for the sample. So that's the probability of a person, one of the six, testing positive. And then here's the question. This is what they want to know. What's the probability that the mixture tests positive? And that's the question we're asking. What's the probability that your mixture tests positive? So you got to go back over here. Because what you know here, by using the fact we gave you for at least one, and very important fact, that this mixture now only tests positive when at least one person tests positive. That's when this mixture tests positive. Now, by the complement rule, that's 1 minus the probability that none test positive. So there we go. 1 minus the probability that none test positive. And so remember, you're selecting 6 individuals. And what that means is we have to compute the likelihood here. The chance that none test positive. So you have to understand the meaning that none test positive. That means they all test negative. Okay, if none test positive, they all test negative. So the statement then is really 1 minus the probability that they all test negative. And we're selecting 6 people. So that's the probability the first test negative. And I'll go through every detail. And the second test negative. all the way through the 6th test negative. And this is and. First test negative. Second test negative. All the way down to the 6th test negative. Now you say, how can I write this without my conditional probability? Because remember the key phrase here and the key idea of this section, that when you test people, when you select them, the results are independent of one another, because this is supposed to be a random selection, So every probability value here is independent of the other. The chance that any individual here, like the first one, testing positive or negative, is independent of the chance that the second person will test positive and negative, and so on. Third person, independent of one another. Fourth person, the chance the fifth person tests positive or negative, that's independent. That's the past, doesn't affect the present or the future. So the prior result doesn't affect the next result. So this is an independent process, and that's also the key. Now, go back here, and this is a very involved question. It's a beautiful question. We just simply need to know, what's the probability? Here's what this comes down to. What's the probability an individual test negative? Now, I don't think they told us, but maybe they did. What they told us right in here is that the probability of an individual testing positive is 0.12. So the probability that an individual tests positive is 0.12. We could now deduce by the complement rule that the probability an individual testing negative is 1 minus the probability that an individual tests positive. Which is 0.88. That's a chance an individual tests negative. So we use the complement rule because this is now 0.88. And this is 0.88. And you end up getting here, at the end of the day, one minus 0.88 to the 6th power, which would be approximately a value. So this is how we answer the question. So we're going to get the TI now, and we're going to try to find this answer here. You say 1 minus 0.88 raised to the 6th power. And if we go out to the nearest 10,000s here, 4 decimal places, the answer is going to be 0.5356. So this is the probability that the mixture, let's go back, it looks like it's 53.56%. That's the probability that the mixture is going to test positive. Yeah. Okay. This is the mixture now, right? Let's label that. So the process is really this, okay? About 53.56% of the time, a mixture of 6 people, 1, 2, 3, 4, 5, and 6, about 53.56% of the time, this mixture is going to test positive because at least one person tests positive. And what they'll do then is, for those cases, they'll actually come back and they'll call each 6 people and they'll retest them. They'll ask each one now separately to retest. And so this is, a sort of cost-saving measure, in all honesty, for just doing, random testing. And in your homework, you have actually other questions like testing water. It's done the same way. So there's a lot of testing that's done, what's called like batch testing, because this is a batch of, in this case, blood samples. So they call that batch testing. They test the batch, and if it's, positive, then they have to go back and retest everyone separately. So they'll do it all over again. They'll go, okay, we got to retest you separately and see what the results are. Next person, retest separately. Third person, fourth person, fifth person, sixth person. So you go back and you actually retest these people, and then you see what the results are. Okay, so that's the idea, so that people are tested twice. You can now say, well, you got tested twice. And in one case, it was the batch, and then the second case, it was individual. But they'll only do that when the batch tests positive. And this is the likelihood that it happens 53.56% of the time. So anyway, it's a very fantastic way to actually, I would say, save money in a testing procedure. Very popular, and I think it's something you guys want to know about. Anyway, let's go now to something else I wanted to look at today, briefly, to show you, related to, this concept of at least one and being independent. So we're going to go back to here. I think it's in my statistics online transition. It was in the lecture we gave on expected value, probability distributions and expected value. So to show you guys again, some concepts here, right? We did the raffle ticket, and so I won't do it again, but you guys have that one in your notes. What I do want to do here, and we did the life insurance question. So you go, okay, there's a life insurance, good. But I want to give you another kind of question here to go over as solutions, and this is the Las Vegas new game. It's called the, I'll call it the 3 Aces game. So these are kind of some questions I've given to people in the past, to look at. So in this particular game, what it says is all you have to do is select 3 different aces. So this is how you win this particular game called the 3 Aces game. So I'm going to put that down here, and we're going to call it the 3 Aces game. And when you gamble, you can either win or you can lose. Okay, so let's set this up. It's a gambling game. You win or lose. These are the outcomes. We're going to talk about probability here, since this is an expected value. So how you win this game is by selecting 3 different aces. So you have to select 3 different aces. So we can compute that probability. 4 over 52, 3 out of 51, 2 out of 50. So this is the probability of actually winning this particular game. So we go back and you go, okay, this is the 3 Aces game. We need that probability. And we'll find out what that is. And of course, we're going to have to approximate. So this becomes 4 times 3 times 2, close this, divided by 52 times 51 times 50. And what you see here is an answer in scientific notation. So what I'm going to start to do is just write this down as 1.8 times 10 to the minus 4, because that's what this is. So we're going to start to approximate here, and I'll show you what I would do. I would actually start to say, okay, what number is this? Since this is, a value to the minus 4 power here, right? We're going to have to move the decimal 4 spaces to the left. And what that means is you'll have 3 zeros. So I'll say 1.8, move this 1, 2, 3, 4 spaces with 3 zeros. And I'm going to approximate this. I can approximate this to this place value, but I think we said the 10,000ths, right? So what this digit becomes here approximately is 1, 2, 3, and then this will be a 2 because the 1 is in the 10,000ths position and the digit to the right is an 8, so we add 1. So this is an approximate probability of selecting 3 different aces here. And that's how we win this game. But you now say, well, what about the opposite of winning, the 2 outcomes in a gambling situation? You're going to lose. So the chance you lose will then be 1 minus, and this is approximately 0.0002. So let's use the complement rule to find the probability that you lose. And this is what you want to do. Okay, you want to actually use that complement rule. 1 minus 0.1232. And we get 0.998. I think that's 3 9s and an 8. Now that's the chance you lose this game. So, okay, we found those 2 probability values. We'll put that up here. And, I might want to change the color here on this. Chance you win, chance you lose. So I'm going to keep this down here for now, just so you guys have that in your notes. And let's go back and really continue this reading from the browser, what this is. They're saying Las Vegas is offering a new game for people to play, and all you have to do is select 3 different aces. It costs $5 for a chance to win $1,000. So it costs $5 for you to win 1,000. Compute the expected value. Costs 5 to win 1,000. So how this works is this way. If you lose the game, right, what you ended up losing is $5. Now, when you win the game, because it costs $5 to play, they may give you a check for $1,000, but you actually netted $995. Now, that was net. Okay? And that's what you always want to use. You want to use the net value. So you netted $995. So this here in the definition of expected value here, here's my x. Here's P of x. When you want to compute that expected value, mu is the sum x times P of x for all x. We use the x value and the associated probability value. So you create this additional column of x times P of x. And the values are going to be 995 times 0.1232 minus 5 times 9998. So we're going to multiply those two values and really multiply those two values, but we're going to add the results. So a couple of ways we could do this. I'll do this a little bit differently here. And, you know, like we're going to add these here. So let me show you directly in the TI. So we have now 995 times point, put 3 zeros and a 2. Now I can say plus a negative 5 times 0.9998. And by doing that, I get negative 4.8. I can also have done the following, because addition of a negative is also known as subtraction. So I could say 0.0002 minus 5 times 0.9998. So notice the keys here. You got subtraction in the second computation. You got the negative sign in the first. So be careful here. You can't, don't mistake subtraction with that negative sign in the calculator. So the expected value is a negative 4.8. And you say, what does negative 4.8 actually mean? Well, that's negative 4.80. So mu here is negative 4.80, which is actually, you owe $4.80 here. So every time somebody plays this game called the Three Aces game, every time someone plays, they're saying to the casino, here's your $4.80. It's a negative expected value game for the player, but it's positive for the casino because they get the money. So the net result, the long run average, is everybody is contributing $4.80 to play this game. And, you know, and that's kind of 2 additional examples I wanted to get to this week. So, you know, I finished this up here for you guys today. Hopefully you guys enjoy it. Hopefully you guys appreciate it. You'll probably see some of these things on your test. So this is why I'm sending it to you guys, because this is some beautiful high-powered probability that's meaningful for all of us in our everyday lives. So take a look at it. And if you have any questions, any concerns or issues, contact me. And we'll see you guys later. Have a great Sunday.